The third talk in the session, we will focus on the vulnerability to faults, which is a very important topic in the case we use AI hardware accelerators in safety-critical applications and mission-critical applications. So this is the outline of my talk. I will make a very brief introduction to accelerators for the different types of neural network models that we use, such as artificial and spiking. I will talk about their vulnerability to hardware-level faults, what can go wrong. And then we will talk about methodologies to perform reliability assessment and techniques to perform fault tolerance. And then in the second part of the talk, I will talk about the work that we do in my group, and we focus on sparking neural networks. Okay, so we address those issues for sparking neural networks. So AI today is in the news. It's a buzzword, and there's a good reason for that. It finds numerous applications, so everybody knows that. The key enabler for AI today is deep learning or deep neural networks. So these are big models that comprise many different layers. They have millions of synaptic parameters, and they perform a myriad of operations in a single forward pass. So typically, those algorithms are run in the cloud on giant farms of servers. But we have an incentive of moving the algorithms from the cloud onto the IoT edge devices. And to do so from a hardware perspective, the main challenge is the shuffling of data from the memory to the processor, okay, that the previous two speakers talked about. And this is something that Damian mentioned in the very end, in answering the last question. So today, widely used accelerators are GPUs and FPGAs, but we can gain over one magnitude of cost, energy, performance improvements by designing ASICs, application-specific integrated circuits. Okay. So why we are interested in performing edge computing, pushing the applications, data, and computing power away from the cloud onto the IoT devices. First, we reduce the data transfer requirements and we save energy. Then we save bandwidth, which is very important because the forecast is that there will be tens of billions of devices connected in the near future. We don't want to do this for low latency. There are many applications like autonomous driving cars. You want to do the performance locally. You cannot afford the latency with communicating with the cloud. Okay. It's also a matter of privacy. You want to handle sensitive data locally. And it's a matter of availability. If you want to have autonomous systems that do not depend on the internet. So GPUs, FPGAs, although they're widely used accelerators, they're too big and they're too power hungry to fit onto many of IoT devices. Okay, that's why we need ASICs. So Damian mentioned this. So the brain is the most efficient computing machine. Another reason we want to build accelerators, and this is from the perspective of the neuroscientist, is to be able to simulate brain activity very quickly, okay, and study the brain. All right, so today we have two main neural network types. The classical artificial neural networks, where the inputs are coded with static values. And the spike neural networks where the input is encoded into trains of spikes. And the artificial neural networks are inspired from the biological brain, but the spike neural networks, they work exactly the same way as the biological brain works. That's why they are termed the third generation of neural networks, bridging machine learning with computing, okay? So the way they work is that you can view them as a capacitor that integrates charge, and they integrate the incoming spikes, and once the spike arrives, then this means that the threshold, the voltage of the capacitor increases, and then when the voltage reaches a certain threshold, then the neuron will give a spike of its own that will propagate to the neurons in the next layer. They also have two other mechanisms which are also met in the biological brain. The one is the leakage. So when a spike arrives and a charge is integrated, then there is a forgetting mechanism. So the neuron the potential will decay a little bit. And the second mechanism is the reset. So once a neuron fires a spike of its own, then its potential will be resetted so that the neuron can spike again, okay? Can be used again. So comparing the two, spiking neural networks, they have low latency, they have high recognition speed, they have low energy consumption because they're event-based systems. But today, the most prevalent solution is the artificial neural networks, and the reason is that spiking neurons are more difficult to design, and also the learning methodologies for spiking networks lag behind the artificial ones. But in principle, they show a lot of potential, but many of those issues, like Damian said, are being researched today. Okay, so neuromorphic chips are here today. Most of these designs are proprietary, or we can use them in the cloud. But it's a fact today, okay? Now, many of the applications where we'll be using AI are safety critical and mission critical. And a good example is the autonomous driving car. So the core technology of an autonomous car will be AI. It will have sensors, gyroscopes, cameras, collecting data from the environment, and the AI system within the car will make decisions where to steer the wheel and where to brake or accelerate. Okay, and the safety standard for cars, the ISO 26262, demands that the error rate is lower than 0.2 failures per 10 to the power of 9 operating hours. Okay, so that's a very strict demand, and to meet this requirement, first of all, we need to have thorough post-manufacturing testing, and we need to make sure that the test escapes are in the order of sub-defective parts per million. But we also need to do in the field self-testing and error recovery during the normal operation. Okay, and the question is, are AI hardware accelerators fault-tolerant? And actually, many people believe that the neural networks we put on hardware inherit the remarkable fault tolerance capabilities of the biological brain. Okay, so our brain can compute with noise, as Olivier said. It can even make up for damage. So why people believe that? Because neural networks are distributed systems, so they think that if a neuron breaks or a synapse breaks, the neural network will still work correctly, because they are inspired from the biological brain, but because they also use over-provisioning. So over-provisioning means that not all neurons or synapses will be used in a computation. Okay? After training, many of the neurons, we have more neurons than we need, more synapses than we need, and many of them will not be used. Okay? But this assumption has been proven false, and there have been many papers recently, many fault simulation experiments showing that neural networks on hardware, they are vulnerable to faults. And what are these faults? So we have, what are these hardware level faults? So there are faults during manufacturing, so we may have process variation, we may have defects. There are faults occurring in the field. We may have silicon aging, radiation. We may have, if our synapses are implemented with memristors, which Damian was describing, the memristors have low yield, and they also have low endurance, right? If you program them many times, they will, maybe they will stop functioning, okay? Now, if faults happen before training, then that should be okay, because typically the neural networks can learn around faults. Okay, so faults before training can be overcome, but if the faults happen after training, then they can have a catastrophic impact on the inference. Okay, so we need to deal with them. So these are the steps of reliability assessment methodology. So first, we need to start with a fault modeling approach. Typically, people use behavioral level fault models, like more abstract fault models, or use stacked faults or bit flips in the memories that store the different network parameters. Then another issue is where you inject the faults. So we can inject them in the neurons, in the synapses, in the memory storing the weights of the synapses. We can inject them in the registers that store the intermediate data during inference. But we can also introduce the faults into the multiply and add operations. Now, the fault insertion level, I mean, clearly, we cannot simulate faults at transistor level. So most works consider injecting faults at an abstract description of the neural network, like a Python code. But there are works that show fault injection at RTL level, gate level. There are works that show radiation experiments on neural networks running on FPGAs or GPUs. A good scenario would be to be able to emulate faults in hardware, okay? And I'll talk about this later. Now, the reliability assessment, the goal here is to identify critical neurons and synapses, in general, identify critical layers and critical parts of the neural network. But the reliability very much depends on the model, on the cognitive task, on the training algorithm, on the data representation. Olivier talked about this. You know, whether you have quantized or 8-bit or 16-bit data representation of the weights. And it depends on the criticality of applications. So some applications can afford some accuracy loss, some others don't. So once we've done the reliability analysis, then we need to come up with fault tolerance techniques to deal with faults that are critical. And there are two types of approaches. The passive fault tolerance, where basically you try to design your neural network such that it's capable of withstanding some faults, okay, by construction. And the active fault tolerance that deals with the rest of the faults on the fly, and it is basically composed of two mechanisms: the self-test mechanisms to detect faults that happen, and the error correction mechanism to recover from faults. And ideally, we'd like to do the error recovery with low latency and preferably without interrupting the application. So what are the fault tolerance techniques that have been studied for AI hardware accelerators? So starting with the passive, a classical approach is to do fault injection during training. So basically, you inject faults during the training procedure such that the network can learn to deal with faults. But a number of techniques, basically what they do is they try to equalize the neuron importance. So by equalizing the neuron importance across the network, and you can do this by imposing an even weight distribution or restricting low value weights. The idea is that you don't have any critical neurons anymore. So if a neuron breaks, then or synapse connecting to the neuron break, it shouldn't be a big problem, right? Because you can kind of equalize the computations that take place in the network. Now, regarding the active fault tolerance, on the testing side, we can design functional tests. We can design, for example, for image classification, we can have some test images that excite the faults. We can do, if we have a digital design, we can borrow techniques from the digital domain, DFT, ATPG, memory-based. We can build on-die monitors that are specific to neural networks. And we can also run software test libraries to test the hardware with a piece of software. Okay? In terms of error recovery, the straightforward approach is retraining, because we know that with retraining we can make up for faults. But this is something very costly to do in hardware, and when you are in the application. So many people add redundancy, for example, from memristor crossbar. You go and add spare columns with memristors. You can bypass faulty elements. You can bypass neurons that become faulty. You can do remapping. So if you can test your memory and you can identify the faulty cells, then you can go and map the most significant bits of your weights, of the words representing weights, into the non-faulty cells of the memory. You can do some selective triple modular redundancy. I'll talk about this. So let me now jump in and talk about the work we do in my group. So we address those issues, in particular for spiking neural networks. This is a kind of an overview of the framework that we have developed. So we start with fault modeling, and we follow a bottom-up approach where we inject faults at transistor level. And then we try to extract faulty behaviors of neurons. You know, what can go wrong at the output of a neuron. And then that way we build a behavioral level fault model that takes into account transistor level effects. So once we have our behavioral level fault model, we design spiking neural networks in the group. And then we have developed an accelerated fault injection framework where, given the behavioral level fault model and the spiking neural network model, we can inject faults in software, but also in hardware. So I'll talk about this. And after the fault injection, we can do reliability assessment, and then we can come up with effective fault tolerance techniques that target the critical faults, okay, those that do have an impact. All right, let me go through these steps very quickly. So this is the starting point. It is a spiking neuron at transistor level. This is an analog spiking neuron, but we could have used any other design. So I won't go into the details of how this works. So, oops. Oh, okay. There's some latency. All right. So starting from this transistor level design of the neuron, we go and inject faults. So faults can be actual defects like shorts and opens, but we can also do Monte Carlo analysis to study process variations using the process design kit of technology. So we inject all these faults, and in the end, to cut a long story short, we observe two types of faulty behaviors for the neuron, which we can group them into catastrophic faults and parametric faults. So the catastrophic faults means that the neuron stops being functional, and those are two common behaviors that we found. A neuron that keeps spiking all the time, even if there's no input activity, and a neuron producing a dead output, so not producing any spike train, even if it's been excited with input spikes. Okay, so these are two main faulty behaviors that we observe. If you do Monte Carlo analysis, then you will see that there are some timing variations in the output spike train of the neurons. So the time to first spike may change, the firing rate may change, but this type of timing variations, we can also see them by some defects. Okay. So now we have our faulty behaviors, and we can go and create a behavioral fault model. So in our models of spiking neural networks, we use the spike response model. So this is the equation that describes the membrane potential. And I won't go into the details, but this equation has a synaptic kernel that multiplies the incoming spikes and a refractory kernel that multiplies the outgoing spikes and basically models the leakage, okay, the refractory behavior of the neuron. So with this model of the neuron, we can implement dead or saturating neurons by acting at the output spiking train. We can inject parametric faults by varying the parameters of the kernel, so we can vary the time constant of the synaptic kernel, or we can vary the threshold voltage of the membrane's potential. And if we want to simulate synapse faults, we can act on the weights. All right. So these are two examples of spiking neural networks that we have designed. One is for the MNIST dataset, so we use a spiking format of the MNIST, which is a standard benchmark. And a second network is for the gesture recognition dataset from IBM. So the way we do our fault injection, so this is in software. So those models are described in Python using primitives from the Slayer and PyTorch frameworks. So the way we do the fault injection is we customize the flow of computations, okay, based on the behavioral model that I showed you before. And we can do large-scale fault simulation acceleration on a GPU. So these are the type of results that we get. So on the left hand, you see results for catastrophic faulty behaviors. On the right hand side, you see results for parametric faulty behaviors. So the message here is that saturated neurons are much more critical. Saturated neuron faults are much more critical than dead neuron faults. So if a neuron saturates and constantly gives spikes, then it can seriously affect the operation of the network. Another observation is that the last layer is the most important, the most critical one. And this makes sense because at the output you have, for example, the MNIST, you have 10 neurons corresponding to the digits 0 to 9. So if one neuron breaks, then let's say if it keeps spiking, so it's going to be the winning class. So if the neuron that corresponds to 0 keeps spiking, it means that the network will always predicting the 0, right? So it will have 20% classification accuracy. And another observation for parametric faults is that those are not as critical. They are critical for the last layer, and for the IBM network ended up being critical for the second to last layer. Okay. So we've done our reliability assessment, and now the question is, what do we do to compensate for these faults? So we came up with this passive fault-tolerant strategy. Basically, we use dropout during training. So dropout is when you temporarily remove neurons during training along with their synapses. And this, what it does is that it distributes the computational load among the neurons of the network. It creates more uniform and sparse spiking activity across the network. So the importance of neurons gets equalized. So if a neuron breaks, then that will have less impact. So after implementing this passive fault-tolerant strategy, we do a new reliability assessment, and this is what we observe. So in short, we observe that we can deal with dead faults, dead neurons that do not produce any spikes, and timing variations in all hidden layers. Okay, which means that now we can focus our active fault tolerance method on detecting neurons that saturate and dealing with faults happening at the output layer, which is the most critical one. So the active fault tolerance for the hidden layer. So what we do is we need to have a method to test neurons that saturate. So this is an offline test. So basically you send the same input stimulus to all neurons in your network, which can be a current pulse. And then at the output, after the input has elapsed, some time has elapsed after the end of the input, then you check if neurons still produce spikes. Okay, and for neurons that still produce spikes, you flag an error. We can also do online tests by adding a small online monitor on a per neuron basis. So this is a simple counter. It can be just a 3-bit counter. That basically what it does is it when there is an input spike, then it resets. When the spike is over, then the counter starts counting. Okay, basically it counts spikes at the output, And if it overflows, it means that there are a lot of spikes without having a new input spike, then it flags an error. Okay, so these are small online monitors to detect saturation. And now the error recovery, how do you recover from faults? Okay, you detect that a neuron saturates, but how do you recover from that? We came up with this fault hopping concept. Now, we know that we can tolerate dead neurons. So the idea here is to translate a neuron that saturates, that produces spikes all the time, into a dead neuron, a neuron that doesn't work. And we can do this by simply adding one transistor that cuts off the biasing of the neuron. It's as simple as that. So with one single transistor, you can recover from a fault. Now, for the output layer that's very critical, we choose to do triple modular redundancy. So for every neuron corresponding to its class, we use 3 neurons instead of 1 in order to be able to implement a voting scheme. And we know that applying triple modular redundancy for the whole network is totally prohibitive, but we can do this for the last layer because it's the smallest layer. Okay, so it represents, for example, the IBM gesture network. It represents 0.04% of all neurons in the network. Okay, so we can afford, with small area overhead, doing triple modular redundancy. I skipped one slide, I think. So these are results with injecting multiple faults, so assuming that many things can go wrong. And you can see that we can tolerate up to 40% of dead neurons for the MNIST network, and for the gesture network we can tolerate up to 10% of dead neurons with minimum drop in accuracy. So this 10% corresponds to hundreds of neurons, right, being faulty. Okay. And do I have time? Or yeah. So now we also have a hardware platform to do fault injection experiments. So we have a convolutional spiking neural network designed in VHDL. And we have all the software routines around it. We can configure it. We can do fault injection. We can create faulty versions of the network. And we can accelerate fault injection, so we can test the faulty version of the neuron in just 1 second. Okay. And this design is based on a convolutional node that I'm not going to go into the details, but the idea is that you have this convolutional node, and looking at the architecture of your network, then you create a 2D mesh, where each point in the mesh is this convolutional node. Okay, so this design is modular in the sense that starting from this convolutional node, you can build any network you want, any number of layers, and any convolutional node within any number of convolutional nodes within its layer. And this particular example now that we're using in hardware is for poker card symbol recognition. So this is the network for poker card symbol recognition. And our fault model for the hardware, to take into account the particularities of the hardware. So we assume bit flips happening in the memories, storing the various parameters. Okay, so most papers in the literature, they do bit flips in the kernel weights. But now that we have a true hardware, we can see what happens with bit flips happening, all over the place. And the framework can support single bit fault scenarios, but also we can do multiple bit flips with some bit error probability. And here are some preliminary results. So here you see that the network can tolerate up to 10 to the power of -5 bit error probability. If the error probability is higher than the network, there's an impact on the classification accuracy. The classification accuracy starts dropping. And if you do single bit flips, where you can study the effect of faults happening in the different parameter types of the network, different layers, and at different bit positions, right? So for this particular design, the weights are represented with 8 bits, okay? So something that we saw, for example, is that those router parameters, so that basically route the spiking events to the output node where they should go, they are very critical, right? If something goes wrong with the router parameters, basically the architecture changes, right? So those are very critical. The network parameters, like the threshold of the voltage, so these correspond basically to timing variations. It turns out that in hardware are not that important. And another observation for the kernel weight, so these represent 97% of the total memory. We see that the 4 least significant bits, they do not impact the accuracy, okay? Which means that if you do like a memory error correction code, I don't know, you can drop those 4 least significant bits and just focus on the 4 most significant bits, and you can save 50% of the cost, right? I think this is all I have to say. So I talked about the vulnerability of AI hardware accelerators to hardware level faults. Talk about how to frameworks to perform reliability assessment and ideas to perform fault tolerance. And thank you for your attention. I'll be glad to answer questions.